Okay, we're going to get started with the afternoon session. So we're happy to have Paolo Benincasa from the Max Planck Institute for Physics, who's going to tell us about cosmological polytopes and beyond.
Thanks a lot. First of all, I would like to thank the organizer for giving me the opportunity to give this talk and to give it on Zoom. Unfortunately, I couldn't travel now, and so I couldn't be there. So the idea of this talk is to actually give a sort of overview of this topic that has been developed since now it's 7 years almost. And the general idea is that together with particle physics, there is another area of high energy physics, which is cosmology, which really serves as a playground for exploring new combinatorial structure. And I will present the one that emerged in these 7 years and how they are connected to physics and why they are relevant for physics. So the general picture of cosmology that studies the origin and evolution of our universe is that we live in a universe that has been evolving, it's been expanding. And so we want to try to understand its evolution, its history. And what we actually do is to observe, for example, the galaxies, looking for patterns in distribution of galaxies, and from them try to deduce what could have happened in the past. Now, there are indications from observation that in this evolution, there was a period which is called inflation, where there was expansion which was accelerated, and this which is indicated by this time. And in this expansion, this expansion actually set the seeds for the structure that we can observe today. In more concrete terms, this means that there are some mathematical quantities, some correlation function, for example, for distribution of galaxies, or the correlation function of the temperature fluctuation in what is called the cosmic microwave background. And this correlation function had some evolution, but this evolution had the initial condition at the end of this period, which is called inflation. And these initial conditions are nothing but other correlation function of a quantum field. So in this talk, we will focus on this correlation function at the end of inflation, at the end of this accelerated expansion period of the universe. And this is physically important for two reasons, because one, as I just said, it gives origin to everything that we observe nowadays, but also it is the endpoint of the evolution in the very early life of our universe. So one big question is actually to try to extract fundamental physics out of this correlation function. And in fact, this is a big question because despite this idea of inflation is very nice and elegant, its physics is really a mystery. And so what we will do is now try to come up with some novel way of computing these objects and try to read off what is the physics that they contain. So this will be the focus of this talk. Now, as I said before, there was some evolution during this period of accelerated expansion, and that at some point ended. And the correlation function typically can be computed as some integral of a probability distribution. For physicists, this is a standard thing that we do in quantum field theory, but this is a general thing. And the probability distribution can actually be written in terms of an object which is called wavefunction, or more using a little bit of buzzwords, the wavefunction of the universe, which is nothing but a transition amplitude from a vacuum state to the configuration that one has at the end of inflation. And so if one looks carefully to this formula, one realizes that this is nothing but a mean correlation function that it's typically characterized, is what one computes for out of equilibrium systems. And as it happens for particle physics, one can do perturbation theory, so one can expand in some small parameter, which is given by the coupling of the interaction. And again, we can use Feynman diagrams to model what happened in this interaction. Because what we know, what we want to compute is this correlation function or the wave function at the end of inflation. But in order to do that, somehow we need either to take into account this evolution or to know some rules that allow us to compute this object directly. And one can try to think that this object is the result of summing over all possible things that have happened in the past. And as I said, they can be modeled by this Feynman diagram. Now, just these look a little bit different from the one that you already saw in during this workshop, because simply what's happened is that now we have a transition function from the vacuum, so from nothing in the infinite past. Then something happened, these interactions here, and then you have something that has been produced and reached this line, which is just let's say the end of inflation. Okay, so now this, for example, it's what is called a contact diagram. This is a three-level diagram, and this is one loop diagram. So this line is just telling you that the states don't go, the particles that have been emitted don't go on, reach at some point some boundary. Okay. So more or less, at least from the surface, things look kind of similar to what happened in particle physics, at least in the way that we can model this this evolution. So in physics, the big questions are whether we can actually understand, put constraints on whatever happened in the past in a model-independent way, which means, which boils down to understand what are the fundamental rules, what are the fundamental principles that any reasonable model has to satisfy. And in mathematical terms, this also boils down in understanding what are the constraints on the analytic structure that this correlation function, this wave function has to have, because these are directly connected with the physics. And this is very important because not only we can describe, we can try to understand the first instance of the life of our universe, but also one can estimate that the energies during inflation can be as large as the upper bound to be 10 to the 14 GeV, which means that is some sort of window of very high energy processes that we will never be able to produce on an experiment on Earth. So these are, let's say, a little bit the physical picture. And what it turned out in this last 7 years is that combinatorics actually can give us a hand, because it has give you another perspective on this on the physics of how the physics encoded in this observable, and actually give us new rules for computing, which means also new go even beyond the realm in which we find this structure. So it's a really from a physics perspective, it's very big opportunity. And from a math perspective, I would say that contrary to all the structure that you have already saw in the workshop, like the Amplituhedra, etc., these objects turns out to be somehow simpler, and maybe they give the opportunity to sharpen a little bit some questions that are in general more difficult to answer if one just want to answer them generally or in a very complex structure like can be the Amplituhedra. So
I assume there's some gravitational background in there.
Yes. So the idea, what we're doing is substantially it's quantum field theory in curve background. Okay, so there is some we need to take into account the fact that there is an expanding background.
The inflationary background, so there's gravitational field plus this inflationary scalar, or because you mentioned inflation implies that there is a scalar that drives that inflation.
Yeah, okay, sure, but there are okay, the viewpoint, which is indeed it's the normal one, is based on a very few theoretical understanding of what happened in the period. Another way to think about it is try to come up some general rules which don't make any reference to try to understand what are the general rules that an inflationary process needs to satisfy, and try to impose those directly on the observables. So what I will do now, which is much low level of what I'm saying now, is taking a large class of toy model, of scalar toy models, in a fixed expanding background, which is a general FRW cosmology, but it's an expanding background, trying to understand new rules for computing them, and trying to see if we can infer some general or almost general lesson about the analytic structure of these objects. So what I will say for sure will hold in a realm of quite large set of toy models, but I wouldn't claim for the moment that actually, I mean, this can be used actually for actually inflationary purposes up to some extra operation that one has to do. But if you want, the general picture is that we start in a very humble way, taking some large class of scalar toy models on an expanding background. And everything that I said before is really the motivation, but yeah, so there will be some extra step if you want to get to make a phenomenological statement. Okay, so this then it's for this large class of the models, which substantially are conformal couple scalar and light scalar in with the polynomial interactions. These graphs can actually be written in a very simple way, just eliminating the external states and everything else, just leaving the core of the graph, and attaching some labels, and some labels for the physicist are just a parametrization of the kinematic space. So this Y here will be the energy of the internal state, and this axis will be the sum of the energies of the external states. Okay, while in this case for loops, they are going to be just a parameterization of the loop moment. And what's happening is that for this large class of toy model, it turns out that every diagram like this can be written in terms of these classes of integral, where you have something which is a rational function indicated in dark blue, which is universal, which meaning that does not depend on the cosmology. Then something which parameterize the loop integration, and another integration over these external energies, whose measure is what really tells us in which cosmology we are. So the choice of the measure will tell us if you are in a de Sitter background, in FRW cosmology, or something else. So in general terms, that measure has the meaning of implementing the specific background. And it turns out that this universal integral, it's the wavefunction of the correlation function of in flat space, and so this integral can be thought as a mapping between the flat space kinematics and the cosmological kinematics. Okay. Now, for power law cosmology, which is a classes of backgrounds, then this measure is simply given as proportional to this power. So this integration is really like a ML transform. Okay, so importantly, between these diagrams that you see here and this formula here, you can realize that the singularities of this integrand, which are indicated, the denominator of these integrals, which are indicated by this QG, are associated to the subgraph, and each subgraph corresponds to a singularity of the integrand, which then can be mapped into a singularity of the integrated function. What turns out to have this combinatorial structure, it's or can be is encoded by this cosmological polytopes that I will describe, is this integrand. Okay. Now, so this is a little bit I wanted to give a little bit big picture of going from the physics motivation to a little bit what is the general object that we will care about. Okay, and so the general, as probably you have heard many times during this during the workshop, there is a one-to-one correspondence between positive geometries and a canonical form with the logarithmic singularities. And it turns out that precisely the canonical form associated with this cosmological polytope has its rational coefficient, the canonical function, which gives you precisely the object that we physically we want to study. Okay. Okay, so this is a general picture. I don't know if there is any question at this point, because now we'll describe a little bit how these things emerge from this general picture.
Sorry, can you again explain this blue thing here? Why is it universal? Actually? Why? So you say it's actually independent of background.
Yeah, because any universal in the sense that any cosmology will have that integrand.
And the function form of Q's is universal, it's independent of their background. Is that what you're saying?
Sorry, say it again.
I say the function form of Q's is independent of the background. Is that what you're saying?
That's correct. Yeah, neither nothing of this rational function depends on the background. It's really the flat. In other words, it's really the flat space wave function, the flat space correction function, depending on what you're caring about. And any wave function, for example, in any cosmology with these classes of states that I said before, can be written in these terms with that specific integrand. And then what really changed, what really changed is this measure here. So for example, going to this power law case, if we were to consider a phi cube interaction in the sitter in 1 + 3 dimension, this alpha will be 1, and so this lambda tilde will be 1. Instead, if you take some other FRW cosmology, this lambda tilde is different, but this object doesn't ever change.
But in usual perturbation theory, the Green's functions are much more complicated function of the background. You contact it
that's correct. Now here there is a trick. So for example, for conformally coupled scalar, the Green functions are given substantially by it's a combination of exponential plus an extra term, which is given by some boundary condition that you need to impose, because in that case the fluctuation do not vanish at the boundary, so you need some extra piece if you are computing the function. Then for this light scalar that I was referring to, the Green function are given instead then in terms of exponentials, they are given in terms of Hankel function. But for some of these light states, this Hankel function can be mapped, are related to the exponential by an operator. So I can actually I can consider my case with my nice exponentials, which is where everything is nicer, doing my calculation, and at the very end, apply these operators to map my result to the light state that I'm interested in. For a heavy states, it's a little bit more complicated, and actually we are working on right now. But so for this reason, I wanted to stress from the very beginning that what I'm saying from a physics perspective has the limitation of being valid for these specific classes of part of scalars involved. Thanks for the question. Any other? Okay, so if not, there is one nice thing about this picture is that there is a one-to-one correspondence between graphs and these polytopes. So we start from again, this is our Feynman diagram. We go to this what typically we call reduced diagram, and as I say, I mentioned before that the singularities of this wave function are associated to subgraph. So one thing that we can do is to take, let's say that we to take this graph, we can associate the weights of the graph, which physically have some meaning, the meaning of the energies. We can think that there are some local coordinate in projective space. In this particular case that I'm taking for illustration, it's just P2. And then all the singularities associated to subgraph determine some lines in P2. Okay. And one thing that I haven't mentioned that there is some condition which is called Bunch-Davies that oblige us to consider not only this positive combination of the energies, but also that each of these variables has to be positive. So this implies that once we draw these lines, the positive condition will carve out in this case this triangle. Okay, so and what's happened, and therefore that equation that gives us this line is nothing but identifies nothing but that one of the facets of this triangle. So this is a way to understand how from a graph, from this particular graph with the two vertices and one edge, we can deduce the existence of this of a triangle. Okay. And so the condition that obviously a vertex is on one facet is that when we contract it with the covector which identifies the facet, this contraction, this dot product has to be 0. Otherwise, if it's not on the facet, it has to be positive. Okay. So as I said before, one can attach to if I focus on this triangle, one can attach a canonical form, which is given precisely by in this case the lines, but in general the hyperplanes which identify the facet which go in the denominator, and then the numerator instead identifies what is called the adjoint surface, which is just the intersection of the hyperplanes containing the facet outside of the polytope. In this particular case, it's easy to see that given that one of the conditions on this canonical form is that it has to be projective invariant, GL1 invariant, by GL1 invariance, one can see that once you put in the denominator all its facets, in the numerator you can just have a number, and by projective invariance it has to be this combination among the vertices. Another property is all the canonical form is that it's the residue along any of the boundaries, any of the facets is the canonical form on the polytope sitting on that facet. And in general, for these canonical forms, the maximal residues has to be plus or minus 1 or 0 if there is no residue there. Okay. And so, and this satisfies this condition. So this is a very simple case to see how this emerges, but obviously one can ask the question, so if I give you some very complicated graph, can I know what is the object associated with it? And as for example, this is a more complicated graph. And one thing that you can think is that precisely you again take all these weights of the graph and they consider them as local coordinates in your projective space. So your projective space will be always of dimension number of vertices plus number of edges. Again, that there is this relation between subgraph and facets. And therefore, the canonical form will be given by all the hyperplanes associated to this to the subgraph that you put in the denominator, and then the numerator will be this polynomial which gives you the adjoint. For example, for the case of the square, the adjoint is just given by a line from this point A, which is the intersection outside of the square of these two lines, and B, which is the intersection of the lines 1, 2, and 3, 4 outside. Okay. Now, there is a more general way of thinking about this, which is if you consider this graph, you can see that this is nothing but taking a collection of this other graph, of these two vertices graph with one line, and identify their sides and the label on their sides. So we know that there is a triangle associated to that to one of these two vertices graph with two vertices graph. So one can think that we have a collection of these triangles, which in principle don't talk to each other, but we embed in the same space. And then what we do is identify some of the midpoints along this two of their sides. Okay, so this triangle will have the feature that they have the midpoints associated to the two sides of the graph, and the other midpoint is associated to the edge. So the general prescription for the construction will be that you can intersect these triangles at most on two of their sides out of their three. So, for example, if you have two of them, we can intersect on this on one midpoint or on two. Each of these intersection is one constraint. So if we embed these two in the same space without talking to each other, this will be in P5. If I impose one condition, the object will be in P4, and this object will be in P3. Now, if I think that each of these correspond to one of these two vertices graph, then it's easy to see that one will give you, when we intersect along just one of their sides, one will get this object, and when I intersect along two, which gives me an object which lives in P3, they give me this other one, which is just the convex hull of what I drew before. Okay, so in a sense, there is a general way to understand and to implement a construction without knowing anything about physics. So in general, the general dictionary is that there is this canonical form, which has a coefficient, which is our canonical function. And if I write this in the specific local coordinates, which are given by the weights of the graph, then the coefficient is precisely the wave function, the contribution to wave function associated to a graph in one-to-one correspondence to the cosmological polytope. Okay, and so there are two, if you like, two challenges. One is to understand the properties of the polytope in of itself, and then understand how these properties translate in the final answer once we do all these integrations. The nice thing is that even the loop integration has also a nice a nice geometrical meaning, because the measure is related to a complex, to the volume of a simplex whose sides are given by these weights. And the contour integration is just a requirement that this volume is positive, but not only the volume of the full simplex, but the volume of each of its faces in all codimension. For physicists, this is the same thing that happens when we look at these representations, which are called like loop tree duality, where you integrate the L0 integration. If then we write this in terms of moduli of momenta, we obtain precisely this type of structure with the contour and the measure given by the same, having the same geometrical interpretation. Okay, so just as a general dictionary before going in what we have learned so far from this construction. So the canonical function corresponds, for example, to the wave function. Then I can ask about triangulations of, if I have polytope, I can triangulate it. And this, from a physical perspective, represent precisely different way of computing the wave function, different way of organizing each order in perturbation theory. So we can obtain what is called the time order perturbation theory or fashion perturbation theory. We can obtain loop tree duality. We can obtain another thing which is called causal representation, and many other which have no name. Then the boundaries are related, given that the facets are related to give you one are associated with singularity. So given going on that facet means taking one residue. Going to high codimension faces means going to high codimension residues of the wave function, which, if you know how these interact with the measure of integration, with contour integration, we can translate the statement on the residues in statement of the residual integrand in statements about the discontinuity of the integrated function. Then there is a very specific facet which is related to the sum of the total energies, that if you go there, then you obtain a polytope, which is a representation of a flat space Feynman diagram. So this even gives you the opportunity to have a different understanding of each Feynman diagram from a combinatorial perspective. And from that, actually, there is a very simple combinatorial proof. I will not go through it now, about unitarity for amplitudes. And then there are things that you can prove from contour integral representation of canonical form. You can prove Lorentz invariance when you go to this specific point, when you recover the scattering amplitude, etc. So there is a very well-defined mapping between let's say the physics that we might be interested in and mathematical questions or mathematical properties, mathematical questions you might ask, or mathematical properties you might be interested in. Okay. So let's a little bit, but in general, maybe study the facet structure or the an arbitrary codimension phase. The structure of an arbitrary codimension phase might not necessarily be an easy task, but here precisely the one-to-one correspondence between graph and polytope give us a hand, because these are the three vertices of the triangle associated to this graph. Then, so as I said before, a vertex is on the facet if when contracted with when its vector is contracted with the covector which identify the facets, it gives you 0. So one can actually associate a marking to the condition of when a vertex is not on a facet. For example, if this Z1 is on the facet, which correspond to having this of taking this subgraph, so taking the facet associated to the, given by this covector, then this marking X tells me that this vertex is not on that facet. And you can make up the same rules for similar rules for the other one. So we know that if I take a look at the facet associated with subgraph, then this Z2 is not on the facet, so the other two are, and so on. And so one know that if given a graph, I'm marking in the middle, this Z1 is not going to be there, and so on. Now, when we consider a more complex graph, given that they are given by triangles that have been identified somehow, the structure of the vertices is gonna always look like this, with this axis, which just tells you are a canonical basis for the space for the projective space where this live. So if I have a graph like this, I can take a subgraph. So the rule is that if I take a subgraph, I have to eliminate all the vertices, I have to mark in the middle all the edges which are inside the subgraph. For in this case, this turns out to give you the what I call the scattering facet, so a description of the amplitude. If instead I take this other subgraph, I will have to mark the rule, the graphical rule will tell you that I will have to mark all the in the middle all the edges inside the graph, but then I have to mark all the edges departing from this subgraph close to the subgraph itself. So this tells me that all these vertices are not on that facet, while the others obviously are. So this is a very easy way to answer the question about what is the vertex structure and more generally, what is actually the combinatorial structure of the polytopes living on these facets. And physically, this is important because we are computing residues. This residues has actually physical meaning. In this case, it's the scattering amplitude. In this other case, what's happened when you consider this combination of energies going to zero, you're requiring that here you're imposing energy conservation that typically cosmologically doesn't hold. And when you are imposing energy conservation, you're saying that this process becomes a flat space amplitude, while whatever is left outside is going to be just some sort of linear combination of lower point wave function. So understanding this actually tells you something about the physics on these singularities. So we can also mark, rather than marking the vertices which are not on the facet, we can mark the one which are on the facet through this circle. So whenever you see this structure where you have this circle close by the vertices of the graph, you know that inside there is some scattering amplitude. In this case, there is a scattering amplitude associated to everything, while here there is just a scattering amplitude associated to this subgraph times whatever is left over there. So you can actually prove that this allows you to give a combinatorial proof of certain factorization theorems which hold for the wave function. You can adopt similar strategy for higher codimension phases. So you can ask, you can take two different subgraphs, eliminate all the vertices which are not in them. And so whatever is left, in principle, might span a higher codimension 2 phase, for example. Nevertheless, then you have to ask the question, well, for real, those vertices are, you have a number of linear independent vertices sufficient to span the space. Okay. And in that way, actually, we can come up with rules for which, given a certain graphs, we know whether they identify an high codimension phase or not. And this, for codimension 2 phases, it's a work done with Andrew McLeod and Christian Vergu, which from a physical perspective, is just a statement about Steinman relation. So you can make a nice proof of Steinman relation, both in flat space, and you can prove that they do hold for these wave functions. And then we extended it for arbitrary codimension to in this paper with William. And there the important thing is that you can identify subspaces of the adjoint, and that can help you actually to have a control to formulate a graphical rule for how to obtain triangulation through subspaces in the adjoint. Okay, so there is a number of things that you can prove. As I said before, you can prove the unitarity in flat space by studying the structure, the facet structure of the scattering facet through, as I said, these overlapping graphs, studying the vertex structure when you consider n graph on top of the graph associated to the scattering facet. And then you will have a very nice combinatorial proof of the Cartesian rules, because if you do that, you will see that there is this graph, for example, which identified an amplitude. This other subgraph, which identify another amplitude because it has these two vertices associated there. And then there are this one vertex is associated to this intermediate edge, which form a simplex, and this simplex is nothing but this measure here that you need because of Lorentz invariance. Okay, so that's that's a very super easy proof, much easier than the usual with the largest time equation of the unitarity in flat space. Okay. Then you can play the same type of game more general and say before you can prove the existence of that this time relation hold for the wave function. You can have an alternative proof same relation for flat space. And then you can make up some general compatibility condition among facets. Okay, and these compatibility conditions among facets are important to know, both which multiple sequential residues are non-zero and which are zero, because the ones which are zero identify subset in the adjoint, as I said before. Okay, so there is a nice a nice formula where this K is just the codimension that you're looking at. This sigma S is the number of facets of scattering facets in which, when you consider these several graphs, your polytope is being factorized, and this n bar indicates the case in which you are erasing all vertices from associated to one of the edges. So it's a very concrete formula that then, once you prove it, you can just directly apply to know what, given a certain number of facets, if they are compatible or not. Now, there is so from a physical perspective, one of the big conditions that in scattering amplitude plays some big role in understanding the physics, in understanding that fix the property, the analytic properties, is what's called unitarity, which is nothing but that the fact that the probabilities as to sum to 1. So one can ask the same question about what is the analog statement in cosmology case. What it turns out, I will just state it, I won't prove it, is that this condition of unitarity is actually encoded in a specific non-convex part of the cosmological polytope, which we dubbed optical polytope, just for the fact that in physics, the optical theorem is what encodes the statement of unitarity. And so if you try to follow the same path to prove the optical theorem, you get to something which has been called the cosmological optical theorem, whose geometrical structure just a very specific non-convex part. And so that's actually give us a hand in trying to a little bit understand better the properties of non-convex polytope. Now, there is a thing that one can do, especially if one has control on the canonical function, is try to define it as a deformation from the canonical function of a convex polytope, and that in this case, this limit is completely smooth because you don't cross any of the actual facets. So there is no singularity that you're crossing. Or the second thing is mimicking what have been learned on the cosmological polytopes in terms of compatibility condition, and ask the question about what are the compatibility conditions on these facets. And so this actually provides a more invariant way of understanding, because one doesn't have to play this game of, I have to think how to deform it to get this and how to do it smoothly. So given some of, and one can implement a marking like we did in the case of the cosmological polytope, slightly modified, because now we don't have all this positivity condition, because this point here lives in a part where now the boundary is given by these four lines, and so a point here will live in a region which is identified by the overlapping of positive and negative regions. Okay, so upon some modification, you can have again the very same graphical rules to determine compatibility conditions. And these compatibility conditions can actually be used, and which are substantially the same of the cosmological polytope. For this reason, I haven't wrote it. And then actually one can use that some sort of definition of this specific class of optical polytopes. Now, as at the very beginning of the talk, I mentioned two physical quantities that you can be interested in. One is called the wave function of the universe, and the other one is the correlation function. The wave function is related to probability distribution, but what really an observational cosmologist will be interested in is in the correlation function, because the correlation function for him will be the initial condition for the evolution to then make contact to what he can observe. Now the question is, there is a natural way that from all this picture we can obtain the correlation functions. And this is an interesting question, because in general there is this formalism of Cauchy-Schwinger formalism used to compute this correlation function, and that can be a little bit intricate. And so the question is whether there is a different way, also different way to formulate the actual problem. Now, an interesting way to think about one of standard polytopes that, like the cosmological polytope that we have been discussing so far, rather than in terms of either convex halo vertices or through the inequalities, one can think in terms of a pair of weight orientation, where the weight will be just the statement that, sorry? Okay. Is given by this product of theta function, where the substantially is very similar to the inequality condition. This is telling you that this weight is 0, 1 dependent, or if you are on a side of this hyperplane identified by this W. And then this if I take some random plane that, for example, go inside the polytope, the discontinuity, if I go towards and this boundary can be 0, 1. 0 if it's a boundary, like if I will consider this W associated to this line, 1 if it's a boundary, sorry, and 0 if it's not a boundary, which in substantially is telling you that this weight, it's 1 inside and 0 outside. Okay, so if it's 1 all over, if I'm taking a line and I'm looking at discontinuity, discontinuity just means that I'm taking the limit and approaching this line from the upper part and the lower part. So if this limit of this weight is 0, then that's not a boundary. In this case, it's not, because we know because of this that it's 1 all inside. And if it's 1, like will be in the case of any of the lines containing the facet, then it is a boundary. And then the orientation it's just given by a top form in projective space with a sigma, which is a sign, global sign that it's an arbitrary choice, and typically one chooses to be positive. In this term, now, if rather than thinking about polytopes in the usual way, we think about polytopes in this way, then one thing that we can do is that, okay, I can modify a little bit this definition of the weights. For example, I can take a certain hyperplanes and then declare that my weight is the same weight of the original polytope, but with the sum of this plane. In this context, there is a nice way to choose this plane, because if you remember, in order to construct a more complicated object, I was intersecting these triangles in two out of their three sides. Then there is a special plane which is precisely given by the line which crosses these midpoints in this specific case. So if I take this, in this simple case, this W tilde to be this line, and I take this sine function, then now my discontinuity is that it's 1 on the usual boundaries, and now it's 2 here, which in a sense amounts this change of weight. One can also think of it is making a polytope subdivision, a polytope subdivision of this triangle, and then change the orientation of one of the relative orientation between these two parts. And now we have an object which doesn't have just the 3 usual boundaries, but also have this other one, which is called internal boundary. And I can compute the canonical function, and it's precisely the cosmological correlator. And if I do a specific triangulation of it, I obtain precisely the way that I will obtain it if I will use the in formalism. So I can play with other triangulation to get maybe other more insightful expression if for whatever question that I might want to ask, or if I want to, for example, put it on a computer for calculating it. So, and there is a last point that I want to make on this is that in the case of standard polytopes, if I know all the intersection of the hyperplane containing the facets outside of it, if I know at least not even all of them, a subset of them, I can actually determine what is the adjoint, and therefore the numerator of my canonical form. And I can do this because, and these conditions are substantially the compatibility conditions that I mentioned earlier. Now, in this case, I can ask the same question. Now, this is the boundary intersect this line here, but I have just one point which satisfies this type of condition. So, in general, compatibility condition determine multi-parameter, in general, in this case, one parameter family, but in general, multi-parameter family of adjoint surfaces. And these parameters are nothing but the weights. So somehow you need to know from the start, or we need to have some other condition to fix these weights. So in other words, the adjoint just is not determined uniquely from the compatibility conditions. Now, a last point I want to make, and then given my time is almost over, I can close, is that one thing that struck me is the fact that we started from some very specific construction, which was the cosmological polytope. We asked some question about just both physics and mathematics, about from a mathematical perspective, which operation we can do on it, obviously to map some properties that we were looking for in physics. But now one thing that we also discover is that if I am interested in studying this integral, which I am because it's actually the final physical problem, then this particular structure, this product structure that gives me the triangle for the integrand in this case, actually tells me a lot about the asymptotic structure, both in the infrared and the ultraviolet. How? Because from it, I can construct a Newton polytope, but now this Newton polytope, through now this Newton polytope has a very specific structure because of these products. It is really a Minkowski sum of simplices, starting from a top dimensional simplex with the lower dimensional, which correspond to 2 out of the 3 sides of the simplex that in P2 is again in a triangle. And so with this idea, you can determine from very easily what is the Newton polytope associated to it, not only its facets, which determine what are the possible divergent directions and how fast the integral diverges in that direction, can be associated to tubings, okay? And the number of tubings for each facet determine how fast it's gonna go to infinity in case diverges. Okay, and the structure, I mean, this is in mathematical literature is known as Nestor-Hydro, but it's a very simple structure that then you can study for arbitrary graphs. You can just because the fact that it's just a Minkowski sum of simplices, and you start from the top dimensional one to a very specific other lower dimensional simplices correspond to subset of facets, very specific subset of facets, is something that is true for any of these graphs. And you can do it at 3 level. And then this makes very easy to use what is called sector decomposition to, for example, focus on some region, because if I'm interested in this, how diverse in this direction, I can, I have to study the sectors identified by these two covectors and these other two, and it makes very easy the implementation of sector decomposition. And so how I can do it for trees, I can do it for loops, with the different thing that now for loops I have the additional condition. I can do the very same game, but at the end I need to make an intersection between all the divergent direction I find and the ones that are allowed by the contour integration. This is, for example, this yellow surface will be where the contour integration lies. So, for example, this means that in the y direction, I can go to infinity just when both y's go to infinity, while here I can go to 0 just from one of the y's and not both of them. So this gives you a very, and this type of structure, I've been studying in math literature, but it represents from a physical perspective a very simplified simplified version of other studies that have been done in the case of Feynman integrals, where all the technology has been already developed and things are kind of more complicated. Here, where things in principle are supposed to be more complicated, somehow things becomes very, very easy. So just for a conclusion, I wanted to give an overview of many things that occurred in these 7 years in many structure and many things that we could understand about certain classes of polytopes, both convex and non-convex, a more direct way to study these weighted geometries, because they were formulated before in the context of Amplituhedra, but then again, the analysis is very much more involved. Here, because of this relation with the graphs, it's much easier to prove a number of theorems. And then this is probably has more value in the case of physics. There is this nice structure, Nestor-Hydra, I just discussed, that give a nice way of understanding the asymptotics of these integrals. As I said, I mean, I talk all the time about relation, one-to-one relation between the structures and graphs. But in physics, especially if I want to go to something more relevant, like gravitons, for example, what is really important will be understanding if there is some combinatorial structure in the sums of the graph. And this is something that is, for me, in my opinion, is one of the biggest problems, which join physics and mathematics, because I think that this will give rise to a completely novel structure, because there are some indications to say that at least if we stick to this type of space of variables, is not going to be a polytope. And I mean, I really would love that to interact, to have more interaction with both physicists and mathematicians to study this, because I think that any mathematical question has some physical relevance and vice versa, and vice versa. So I can stop here.